Hi, today I will be talking about why so many drugs resemble the structures of neurotransmitters like serotonin and dopamine. The two neurotransmitters, serotonin and dopamine, play important roles in our brain and body. Serotonin is mostly known for its regulatory functions. It helps control appetite, sleep, and mood. It also acts as a hormone in the gut. Dopamine, on the other hand, is heavily involved in movement and reward. It's the neurotransmitter behind the feel good sensation. Dopamine also serves as a precursor for other important chemicals like norepinephrine and epinephrine. These neurotransmitters are important to many bodily functions, which is why drugs targeting them have such a great impact. Now let's look at the Lewis structure of these two neurotransmitters. First, the similarities. Both neurotransmitters feature an aromatic ring which provides stability and plays a key role in receptor binding. They also share functional groups like hydroxyl and amino, which contribute to their polarity and ability to form hydrogen bonds. Serotonin has a more complex ring structure known as an enol ring, which includes a 5-member nitrogen-containing pyrrole ring fused to a benzene ring. Dopamine has a simpler benzene ring. There is also differences in their side chains. Serotonin's side chain is longer. It connects to an amino group further from the ring, while dopamine's chain is shorter, giving it a more compact structure. Now let's explore the relevance to chemistry. Drug receptor interactions depend on electron distribution and bonding, which influence how tightly a drug binds to its target. Polarity plays a big role too. It affects solubility and how well the drug interacts with hydrophilic or lipophilic environments in the body. Forces like hydrogen bonding is important for stabilizing these interactions. The pH of the environment and the ionization state of the drug also lets us know how effectively it can bind. And lastly, thermodynamics, which involves energy changes like enthalpy and entropy. Together, these factors guide the design of effective drugs. This slide focuses on the importance of solubility and molecular polarity for crossing the blood-brain barrier. The blood-brain barrier is highly selective, which means that it only allows certain molecules to enter the brain. For example, L-DOPA used in Parkinson's treatment crosses the blood-brain barrier to increase dopamine levels. Dopamine itself is too polar to cross, which is why L-DOPA, a precursor, is used. Lipid solubility is important here. The blood-brain barrier is lipid-rich, so non-polar drugs pass through more easily. In contrast, polar drugs dissolve well in water. Let's look at how drugs work on serotonin and dopamine. SSRIs like Prozac keep serotonin in the brain longer, which helps depression. For dopamine, L-DOPA boosts levels in Parkinson's patients. Dopamine agnostics mimic dopamine and activate its receptors, and stimulants like amphetamines make the brain release more dopamine. And so basically, each drug is designed to fix problems with these neurotransmitters. Overall, drugs resemble serotonin and dopamine to work like them or affect their pathways. Their structure and chemistry helps them target the brain and treat conditions like depression or Parkinson's disease.